Hello friends, now we are deriving an equation for potential due to a charged spherical shell. We already derived an equation for what is electric field due to a charged spherical shell. By the time we seen that electric field inside the charged shell is 0 and outside it is inversely proportional to square of distance. And electric field due to a charged shell is just similar to the charge produced by a point charge, as if all the charge is concentrated at the center. We are using the same concept to derive the electric potential. Suppose we have a uniformly charged spherical shell of radius r. This is a spherical shell which is charged uniformly throughout the surface, having a surface charge density sigma. First we have to find what is electric potential at a point P, which is at a distance r from the center of the shell. We know that what is electric field at a point P? What is electric field at a point P? That is equal to 1 by 4 pi epsilon 0 q by r square. As if all the charge is concentrated at the center, and potential due to that charge is equal to, or electric field due to that charge is equal to 1 by 4 pi epsilon 0 q by r square. We are using the same concept here also. The electric potential at point P, if the entire charge is concentrated at the center, that's equal to V is equal to 1 by 4 pi epsilon 0 q by r. This is at a point outside the shell. Outside the shell, electrostatic potential will be equal to V is equal to 1 by 4 pi epsilon 0 q by r. If entire charge is at the center of the shell instead of on the surface, if it is concentrated at the center, this is the potential. Okay. Now, if the point is on the surface of the shell, we can write, instead of r, we can use capital R. That is, V on the surface of the shell is equal to 1 by 4 pi epsilon 0 q by r. This is the value of potential due to the shell on its surface. V on the surface is equal to 1 by 4 pi epsilon 0 q by r. Outside the shell, potential is somewhat less than this value, 1 by 4 pi epsilon 0 q by r. On the surface, it is 1 by 4 pi epsilon 0 q by capital. Now, if the point is at inside the shell, if the point lies inside the shell, what is electrostatic potential at this point? So we have a relations between electric field intensity and potential. E is equal to minus dV by dr. E is equal to minus dV by dr. We already proved that electric field is equal to 0 inside the shell. For any charged shell, the electric field inside the charged shell is equal to 0. So E is equal to 0. On the right side, we have minus dV by dr. If V is constant, the derivative of a constant is equal to 0. So we can write as E equal to 0 because V is constant. What does it mean? The potential inside a spherical shell is always constant. Potential inside a spherical charged shell is always constant. Its value is same as on the surface. That is, potential inside the shell is equal to 1 by 4 pi epsilon 0 Q by R itself. Everywhere it is constant, everywhere inside the shell. Whatever the point inside the charged shell, the electric potential is constant because electric field is equal to 0. It is equal to 0 because of V is constant. V inside is equal to 1 by 4 pi epsilon 0 Q by R. That's the potential inside the shell, and the potential on the surface of the shell is equal to the same. E is equal to V equal to 1 by 4 pi epsilon 0 Q by capital R, and outside the shell it is 1 by 4 pi epsilon 0 Q by small r, where small r is the distance to the point from the center. Now let us see how potential is varies with the distance from the center. If you are plotting a graph here, okay, if you are plotting a graph, how potential is varies with the distance. This is our spherical shell of radius capital R, this is the center, and on this axis we are taking the potential, and on this axis we are taking the distance from the center. And inside the shell, up to the surface, this is surface, it's up to the surface what V is constant and maximum value. Suppose this is that maximum value of electrostatic potential. What is value? V is equal to, here the value V is equal to 1 by 4 pi epsilon 0 Q by R. Up to the surface it is constant everywhere, 1 by 4 pi epsilon 0 Q by R. And when R is greater than capital R, when the distance is greater than capital R, now the point comes outside the shell. For outside, V is equal to 1 by 4 pi epsilon 0 Q by R. It means with the increase of R, V decreases. This is how potential is decreases for a spherical shell with a distance from the center. Up to the surface, okay, up to starting from 0 to capital R. When R is equal to 0 to capital R, potential is constant. When R is greater than capital R, potential is decreases with the increase of distance. This is a variation of electric potential to a charged spherical shell.